so this is notebook 9. It's called Julia is Fast, and the purpose of this notebook is to do some benchmarking. To get good statistics, sometimes running benchmarks isn't an instantaneous sort of thing, and so I pre-ran this one, and then we'll scroll through and uncover the results as we go. So the purpose of this notebook, or rather one of the things we're going to do in this notebook, is look at different implementations of the sum function. So this sum function is going to take a vector, and it's going to add together all the many elements of that vector. Now we're going to look at implementations of this sum function from C, Python, and Julia. Now in particular, we're going to look at 2 different versions from C, which are both handwritten. The first will have no optimizations, and the second will be compiled with the fast math flag. Then for Python, we're going to look at the built-in version of the sum function, the numpy built-in version of the sum function, and then also a handwritten implementation that uses the same algorithm as the handwritten one in C, again without optimization. And then finally we'll look at 3 different versions in Julia. We're going to look at a built-in version in Julia, a handwritten in Julia, and then a handwritten that we've optimized a little bit using single instruction, multiple data. And so we'll get started with that now. So we can first generate a vector A with 10 million elements that we're going to use for all of our benchmarking purposes. So we're creating A with this rand command here. And as a sanity check, we're calling the built-in version of sum from Julia on A to see that sum is giving us what we might expect our output to be. And so here when we call sum on A, which is 10 million elements, we basically get 10 million times whatever the average number in the vector A is, which should be about 0.5. And so we would expect to get an output of about 5 million, and that's what we get. So this is giving us sane behavior. Now to do benchmarking, we're going to use a package called benchmark tools. We do have the option for timing things in Julia to use this @time macro, which will tell us how long the code following that macro took to run. The thing with the @time macro is that because there are other things going on my machine, for example, and just variability from one run to another, we're going to see higher variance in how long one run takes versus another. And we see that here. When we call sum on vector A 3 different times, we get 3 very different numbers. So benchmark tools has been created to give us a better way to benchmark that provides some statistics on every piece of code. So we'll run that piece of code many times, and it's a variable number of times depending on how long it takes for the average time to converge. So it runs a piece of code many times, gives us many samples, and then it provides some statistics on what the average runtime was, the best runtime, the worst runtime, so we can have a better sense of what the performance of that code looks like on average, and in a best case and worst case scenario. So here we're using benchmark tools, and we're going to start by looking at our implementations in C. First, just the regular unoptimized handwritten version in C. And I didn't write this notebook myself, I should say, so you're welcome, like me, to treat much of the C code here and the compilation flags as black magic. Even if you're treating this as black magic, one of the things that's cool here is that we are declaring and compiling C code from within a Jupyter notebook. So this is our C code. This is our implementation of sum, and we're compiling that here. And once we've compiled it, we're using this C call function to call out to some precompiled C function or C library basically, and we are assigning it to this function called csum, which is going to work on arrays within our current scope. And so we call csum on our vector A here, and as just a sanity check, and we see that we get about 5 million. As another and better sanity check, we see here how the output of csum called on A relates to the built-in version of sum from Julia's output on A. And we're doing that using this isApprox function, for which the documentation is shown here. If you do !isApprox, you can see that isApprox will compare 2 numbers and check to see that they're the same within some tolerance that you can specify yourself if you're interested. And then these curly braces here are a way of calling the isApprox function. Here, one of the things that's being shown is just what the actual difference between csum's output and sum's output is. And a final thing before, or I guess here, first we benchmark. So we're using this @benchmark command from the benchmark tools package. we're calling that on the function csum, and we see that our best case runtime is under 12 milliseconds here. So what we're going to do is we're going to take that best case scenario extracted from our output from benchmarking, and we're going to add this best case scenario after normalizing to get rid of milliseconds. We're going to add that best case scenario to this output dictionary D, which is going to store all of our results so that at the very end we can compare in a clean way how all the different implementations worked. And the last thing that we're showing here, just to give you a little bit more of a sense of how Benchmark Tools is working, is a histogram on all the different run times from various samples on calling csum, how long these different runs took. And so we can see that there's quite a bit of variance in how many milliseconds this took, from roughly 11 to maybe 19 milliseconds. And we can see that the average runtime is about in here, and it's again this best case scenario from down here that we're actually going to be using for a strict comparison between the different implementations and different languages. Okay, so now that we've looked at the handwritten version of C with no optimization, we'll add a bit of optimization by compiling the same code that we did above, but we've now added this fastmath flag. And now we're getting this function called csum fastmath in Julia. And when we benchmark that, we see that now we've cut our runtime by more than a factor of 2. So we're down to just under 5 milliseconds now for this somewhat optimized version in C. So we're adding that to our output dictionary, and then we will move on to our implementations in Python, starting with Python's built-in version of sum. Now we're going to grab built-in functions from Python using the pycall package here. And pycall gives us this function called pybuiltin, to which we pass the name of the function that we want to grab. So we're grabbing sum from within Python, calling it pysum in our current scope. Here we're doing a couple sanity checks to make sure that pysum is operating the same way as our other sum functions. And then we benchmark pysum. And when we benchmark pysum here, we're seeing the built-in version of Python sum is taking about a second. Okay, so we add that to our dictionary D, and then we can move on to numpy. To grab functions from numpy, we're going to use this conda package, and then this pyimport command to specify which function we want from numpy. We do our sanity checks a little bit later down here. But before that here we're benchmarking, and when we benchmark this we see that it takes about 5 milliseconds for numpy's version of sum to work. So it's much faster than the built-in version in Python because numpy has more information about types and how to work with arrays. So we add that to our output dictionary D, and we see that Python's numpy is performing comparably to C fastmath at this point. Which makes sense because numpy should have optimized C code running under the hood. And I should say that even with benchmark tools producing statistics that give us more precision than say the @time macro would, we are still going to see some variation from one benchmark with benchmark tools and another. And so for example, the amount of variation that we see between Python's numpy here and C with fastmath, I wouldn't say is a very meaningful difference. Or perhaps I wouldn't feel confident saying that it was meaningful at all, to the contrary. So lastly, for Python, we will look at a handwritten implementation of Python, Python sum. And so to do that, we're enclosing our Python code inside a string here, and then we're using this py keyword to indicate that this is some Python code coming up. We use that py keyword here as well. And then we're calling this Python function sumpy in our current scope. And we benchmark it here and see that our handwritten implementation is taking about 1.2 seconds here. So that's our slowest one so far, as we would expect. Yeah, given that we haven't optimized it and it's a relatively simple algorithm. So we add our Python handwritten to our output dictionary D here. And then we can move to our implementations in Julia. So we'll start by looking at our built-in version of sum from Julia. Now that built-in version is just named sum, and what this @which command will do here is tell us where we can find sum or which version of sum is getting used. So it's telling us that sum is written or declared inside the file here in the base language. And if you were to go to this file, what you would see is that sum is actually written in Julia itself, so it's not implemented in like a lower level language. A lower level language like C or Fortran. So when we perform our benchmark on our built-in Julia, we see that that is taking about 4.8 milliseconds. We add that to our output dictionary, and we see that that's performing comparably to C with the fast math flag here, and also comparably to Python's numpy, which has, again, optimized C code under the hood. So we can move now to our Julia handwritten, which looks pretty similar to the Python code that we wrote above. And when we benchmark our handwritten version of this sum function in Julia, we see that it's taking just under 12 milliseconds, which is comparable to this handwritten version in C, which also wasn't optimized. And finally, we can move to our handwritten version of Julia using SIMD. So we use single instruction multiple data by just adding this @SIMD command in front of our for loop here. And adding that small additional syntax to perform this optimization, when we run a benchmark on this, we see that we've taken our handwritten Julia down to the performance of our optimized or our built-in version of sum within Julia. And so we add that to our output dictionary, and then we can order our results and see how everything did. And really the takeaway here is that, first off, there are multiple takeaways. One of the takeaways is that our optimized Julia code is performing comparably to our optimized C code. Similarly, our unoptimized Julia code is performing comparably to our unoptimized C code. Beyond that, another thing that's cool is that, just working with our Julia handwritten code, or, writing something in Julia ourselves, which is something we will necessarily have to do once we start working with more complicated operations and want to write things that are custom. Doing that, we're getting speed and performance that is roughly, it's here a little bit more than a factor of 2 slower than here. I meant to show the built-in one, but that factor of 2 really isn't like that big of a difference. It's amounting to performance of a few milliseconds, whereas if we were to look at, for example, the difference in performance between like Python's numpy, where we very well might go to get speed out of Python versus something that we might write custom in Python, the difference there between what has been optimized via more time and investment and what we've just sort of written on the fly is much larger. So that is our Julia is Fast notebook.